Module 3.3, what we want to talk about, what we want to introduce and discuss, is the idea of continuity. Continuity relates to our limit problems. It's also a foundational concept throughout the rest of calculus. I've mentioned already in the write-up for this module in the videos that limits are really the foundational piece of calculus. They help us form the definitions for other processes that we'll use, derivatives and integrals later in this semester. Continuity is also going to be an important part of any of those definitions and theorems that we encounter throughout the course. So what we want to start off by talking about is what we mean when we talk about continuity, or what does it mean for a function to be continuous. So these are two functions that we've talked about in the last two modules. We want to discuss where is each function smooth and continuous. So we haven't talked about a formal definition for continuous, but essentially what we want to look at is where are there no holes or breaks in the graph. So starting with our graph on the left, we have a couple of different places where we have some holes and breaks in the graph. So our first break would be at x equals -4. Because as we trace along this graph, we hit -4, now we're hitting a point where this function jumps and continues down here. So I actually refer to that as a jump discontinuity, but it's enough just to say that there's a break in the graph. So we would have our next break. We could continue along, no holes, no breaks in our graph, until we get to x equals 2. And then we have another jump or break in our graph. So we have a break at x equals 2. And then we could continue along, and then we'll hit another hole or another break, in this case an open circle, so a hole in the graph at x equals 4. So when we're talking about this idea of no holes or breaks, where is our function smooth and continuous, we're interested in where could we trace this function without picking up our pencil. So right here, we would have to lift the pencil off the paper to continue our trace. As we start getting closer to x equals 2, again, we can't trace any further without lifting our pencil off the page and continuing that trace. The same thing happens even though it's just for one point, just for that instant, but right at that break in the graph, we have to pick up our pencil because we can't draw through that. The function's undefined there, and then continue tracing from there. So when we're talking about smooth and continuous, we're talking about where can we trace our graph without having to pick up the pencil. So in our second graph, we can consider the exact same thing. We can trace along this graph. We could trace this all the way to negative infinity if we could keep going. So as we trace along this, this is a smooth line. We don't have to pick up our pencil until we get to this break, this vertical asymptote. So in this case, we would have a break at x equals 1. And then on the other side of x equals 1, we could pick this graph up. We could continue tracing it and just keep going and going on to positive infinity. So we're interested in finding those places where we can identify holes or breaks in our graph to answer the question informally, where can we trace the graph without picking up the pencil? Typically what we want to talk about is where our function is continuous. So rather than listing the individual points where our function is not continuous, which is what we did above, we listed the individual points where there's some break or hole in the graph. Instead, what we want to do is describe or list the different intervals on which our function is continuous. So taking a look at our graph again, we can trace this section of our graph up to and including that function value of -4. So up to a function value of 3. So as x increases from -infinity all the way up to and including -4, our function is continuous. So for that graph on the left, our first interval of continuity would be -infinity up to and then including -4. So we use that closed bracket. And then using what you have hopefully seen in classes before, but the union symbol or the union notation. So meaning that our function is continuous on this first interval, also on the second interval and third interval, however many additional intervals we join together with that union symbol. So our next interval would start at x equals -4, but we would have an open circle here, so a rounded bracket, and then that would continue all the way up to x equals 2. In this case, we have a filled-in circle, so we would have a closed bracket. So from open -4 to a closed -2. And then we would use that union symbol to join our next interval, which would go from 2 to 4. We would have another break, and then from 4 to positive infinity. So that will go from 2 to 4, and then a union symbol, 4 to positive infinity. With the second graph that we have listed above, we only have this one point of discontinuity, that line x equals 1. Since our function can never hit that line, can never cross that line, in this case we'll have open intervals for both intervals of continuity. That function will be continuous from -infinity to 1, union 1 to infinity. So we can trace along that graph from as small of a value as we want up to but not including 1. Then we could jump to the other side of x equals 1, continue not at 1 itself, but very, very close, and continue tracing that graph up to positive infinity.